Hello and welcome. There are lots of different probability distributions, and this week we're going to talk about just two of them, the normal distribution and the binomial distribution. In this lecture, we're going to start with what is arguably the most important probability distribution in all of statistics, the normal distribution. This is an example of a normal distribution. This kind of distribution is unimodal. It has a single peak. In perfectly normally distributed data, the mode, the median, and the mean are all exactly equal to one another. A normal distribution is symmetric, so observations trail off at an equal rate to either side of the mean. A normal distribution is also known as a bell curve because of the way that the distribution is shaped. Lots of variables are distributed nearly normally, but the normal distribution is an ideal type. There is no data that is distributed exactly normally. Our notation for the normal distribution is n parenthesis mu sigma. This means that this is a normal distribution with a mean equal to mu and a standard deviation equal to sigma. So these parameters, mu and sigma, tell us where the normal distribution is centered, what the mean of the data is, and how wide the distribution is, so how far its spread is. And those are the two parameters that determine the shape of the distribution. A classic example of a variable that is distributed nearly normally in reality is height, and specifically height of a homogeneous population. So for example, we would expect the heights of adult males in the United States to be nearly normally distributed. We would also expect heights, for example, of 10-year-old girls in the United States to be nearly normally distributed, though with a different mean and standard deviation than a different subset of the population. So here what we're looking at is a distribution of male heights in the United States. And then superimposed on that, we also have some lines that illustrate what people say their heights are in their dating profiles on OkCupid. So what we can see is that the distribution of men's heights in the United States is centered at around 5'9", and it's got a standard deviation of maybe around 3. There's a dotted line that shows the actual data for the heights that men say that they have in their OkCupid dating profiles. Superimposed on that is this sort of implied normal distribution that takes that raw data and sort of smooths it into a normal distribution that looks pretty close to it. And the interesting thing that we see here is that the distribution of what the heights that men say they are in their dating profiles is shifted over from the height distribution of men in the United States. So this implies one of two things. One is that maybe shorter people don't use OkCupid, but probably more likely is that almost universally people like to add a couple of inches to their dating profiles. So maybe indicating that people exaggerate their heights, men try to make themselves seem more attractive to other users of this dating website by saying that they're a little bit taller than they actually are. If we take a look at the dotted line, again representing the actual data from this OkCupid study, you can see that starting at around 5'8", that dotted line starts to skew even more to the right. So at about that point in the distribution, what that indicates is that these men are adding more and more inches to their heights. They're exaggerating a little bit more, sort of stretching toward that 6-foot tall benchmark. And then the dotted line falls out and almost exactly follows that implied normal curve all the way out to the end of the distribution. The heights of adult women is also a variable that we would expect to be distributed nearly normally. And interestingly, when we take a look at these two distributions, the distribution of women's heights in the United States and the distribution of the heights that women say they are in their online dating profiles, we see almost the same relationship, that the distribution of actual heights is shifted to the left of the distribution of the heights that people say they are. So that indicates that just like men, women are more likely to say that they are taller than they actually are in their dating profiles. So those are just some fun examples of data which are normally distributed. Let's move on and talk a little bit about what normal distributions with different parameters look like. So again, the parameters of a normal distribution are the mean and the standard deviation. These tell us how the distribution is centered and how it is spread out. So toward the left side, the distributions on the left of this slide, I have normal distributions with a mean of 0 and a standard deviation of 1. And on the right side, distributions with a mean of 19 and a standard deviation of 4. So the top set of graphs here show you the differences in how the mean centers the distribution. So on the left, the distribution has a mean of 0, so on the number line it's centered on 0. And on the right side, the distribution has a mean of 19, it's centered on 19. Below that, we plot these two distributions on the same number line, so an x-axis with the same scale, to show us how the different standard deviations of the distributions affect how they are spread out. So a distribution with a smaller standard deviation, a standard deviation of 1, is taller and skinnier, the data is less dispersed around the mean. And to the right, the distribution with a standard deviation of 4 has more data that is farther away from the mean because the standard deviation is higher. One really interesting and useful thing about normal distributions is that even when those distributions have different means and standard deviations, we can compare them directly to one another. So let's motivate this discussion by talking a little bit about a particular example. Let's say that you are a college admissions officer and you're trying to compare two different students who've taken two different standardized tests. One student has taken the SAT and scored an 1800, and the other student has scored a 24 on the ACT. How can you tell which of these scores is better? Well, the SAT and the ACT have scores that are distributed about normally. So what we're going to do is we're going to compare these distributions to each other, not by comparing the raw scores, but by first standardizing and comparing what are called z-scores. What this means is that we're going to consider how many standard deviations above or below the mean a particular score is. So in the SAT, the mean of the SAT distribution is 1500 and the standard deviation is 300. The mean of the ACT distribution is 21 and the standard deviation is 5. So we're going to follow a particular formula that takes the observation minus the mean divided by the standard deviation. We'll talk about this formula a little bit more on the next slide. But first, let's go ahead and compare these two observations directly. So the score for the first student is 1800 minus 1500. The observation, the student scored 1800, minus the mean, 1500, divided by the standard deviation, 300, which is going to give us 300 divided by 300, which is equal to 1. So 1 standard deviation above the mean. Now the second student scored a 24, the mean was 21, and the standard deviation is 5. So we take 24 minus 21 divided by 5, and we find that this observation is 0.6 standard deviations above the mean. So if we look at a distribution, we can see that one of the students is 0.6 standard deviations above the mean, the other student is 1 standard deviation above the mean. So the student who took the SAT has actually done better in the grand scheme of things than the student who took the ACT. By calculating how far away observations are from the mean of their distribution, what we're doing is calculating something called the standardized score or the z-score. And again, this is the formula for the z-score, the observation minus the mean over the standard deviation. We could calculate an observation minus a mean over a standard deviation for any distribution that we're looking at, but it's only when distributions are normal, when the distributions follow these particular rules, that we can directly compare those z-scores and calculate the percentiles of where people fall in their normal distribution. And for your reference, observations more than 2 standard deviations away from the mean of the distribution, so those observations with a z-score that is greater than 2, either 2 standard deviations below the mean or 2 standard deviations above the mean, those observations are ones we consider unusual. So that is a quick introduction to the normal distribution. We're going to be talking a lot more about this kind of distribution in the next couple of videos, so I will see you then.